Welcome back to another explainer. So let's just jump right into it. What if I told you that the standard way we're training our absolute smartest AI models today might actually be holding them back? I mean, we are spending massive amounts of computing power trying to force these incredible models to perfectly mimic human demonstrations. But there's this groundbreaking new paper that introduces something called the Q-target framework and a new method called TARGET-SFT. And it completely flips the script on supervised fine-tuning. We're going to really dig into the exact mechanics of why rote memorization is failing AI and how this new mathematical lens actually fixes it.
To get a solid grasp on all this, we're going to move through 4 key areas today. 1. The one-hot problem. 2. A unifying lens called Q-target. 3. TARGET-SFT, which is the best combo. And 4. The proof in the data.
Okay, Section 1. The one-hot problem. Let's look at the fundamental flaws in current training.
So I want to pose a slightly provocative question for you. What if teaching an AI the quote-unquote right answer actually makes it dumber? Think about it. When an AI model finishes its initial pre-training, it has essentially read the entire internet, right? It possesses this massive, deeply rich prior knowledge base. But then, during the next phase, fine-tuning, we often hand it a specific dataset and say, hey, say exactly this word in exactly this order. But wait, what if there are multiple totally correct ways to solve a math problem? By forcing the AI to memorize a single specific phrasing, we're actively ignoring and sometimes literally overwriting the brilliant prior knowledge it already has.
And that brings us to Standard Supervised Fine-Tuning, or SFT. Let's define this really clearly. Standard SFT is a process that maximizes the likelihood of every single token or word in a demonstrated trajectory. It strictly assigns a probability of exactly 1 to the observed word in the dataset and an absolute 0 probability to all other alternatives. In the machine learning world, we call this a one-hot target. It relies on this incredibly rigid assumption that every observed dataset token is uniquely and absolutely correct.
Which actually brings up a brilliant illustration of the problem. Think about human education for a second. One-hot SFT is essentially the equivalent of forced rote memorization. It's like a teacher banging a ruler on a chalkboard, demanding you memorize a textbook word for word. But ideal SFT, that should be way more like an adaptive expert tutor. Especially in complex reasoning. Stuff like math or medicine, multiple problem-solving paths are entirely valid. The exact same prompt can admit totally different stylistic choices, intermediate steps, and phrasings. Forced rote memorization just induces overconfidence, it amplifies noisy data, and ultimately it really hurts the model's ability to generalize to new problems.
Moving on to Section 2, a unifying lens. Let's introduce the Q-target framework.
Now, let's take a really close look at this overview, because it completely reframes the entire training process. Usually, AI researchers obsess over the loss objective. That's the mathematical penalty function you see on the left side. But as this diagram points out, the loss is merely an optimization surrogate. What we really need to care about is on the far right, the induced target distribution. Instead of just looking at the loss in isolation, we absolutely must analyze the target at the token level. If a dataset token is noisy or ambiguous, the target shouldn't be a massive singular spike on one specific word. Instead, it should be a softer curve that allocates some probability to other valid alternatives.
If you look closely here at the spreading arrows and those gradients moving away from the model's output, you'll see exactly how this works. At any given token position, the SFT loss objective produces these specific gradients. They act as the core update signal, effectively pushing and pulling the model's internal logit scores, which are represented by those nodes on the right. Basically, these gradients are the invisible hands actively shaping and molding the model's next token distribution.
And here is the direct result of those spreading gradients, the induced target density curve. Notice the stark contrast we're looking at here. That sharp red spike, that represents standard one-hot SFT. It's a single, infinitely thin, completely rigid target. But a more intelligent training setup induces a much broader density curve, like the green one you see right here. It still places a high probability on the correct answer, sure, but it gracefully slopes down to give partial credit to other highly plausible alternative words. It's way more nuanced.
So how do we actually achieve this beautiful sweeping curve? Well, the authors introduced the Q-target framework, and this is the crucial formula that actually replaces that rigid one-hot assumption. Now, don't let the math intimidate you here. Let's completely de-dragonize it. Q sub t is our new target. It simply equals gamma times the dataset token plus 1 minus gamma times the alternatives. Honestly, just think of it as 2 basic questions. Gamma represents trust, like how much do we actually trust the exact word in the dataset. And the second half represents alternatives, meaning if we don't trust the dataset word 100%, where exactly do we allocate the leftover probability mass? So the main takeaway here is that this framework cleanly decomposes all fine-tuning supervision into two very explicit design choices. Choice 1. How much should we rely on the observed token? We just use a value between 0 and 1 to scale our trust. Choice 2. How do we allocate alternatives? We have to specify exactly which other words make sense in that context. And what's wild is that this simple lens actually unifies a ton of existing, seemingly completely unrelated AI training methods into one single, coherent design space.
All right, Section 3, Target-SFT. Let's look at the ultimate training combination.
Now, this comparison right here is the absolute core of why standard methods are falling short. On the left, we've got the loss gradient, and on the right, the induced Q-target, which is plotted against the model's current probability. Take a look at the dark blue line representing standard SFT. Notice on the right, it demands a target probability of exactly 1.0. Literally, no matter how confident the model already is, it's totally rigid. Now compare that to the orange line. That represents a popular alternative called P-loss. With P-loss, if the model is highly certain, the target approaches 1. If it's uncertain, the target drops. But here is the fatal flaw with that. When P-loss drops the target probability, it leaves that residual mass totally underspecified. It just defaults to whatever the student model was already thinking. That weakens the training signal without providing any real corrective guidance.
And you know what? That is exactly where Target-SFT makes its genius move. Enter the teacher model. To fix that underspecified residual mass, the authors introduce a concept called teacher-guided reward shaping. Basically, when our formula decides we shouldn't strictly trust the dataset label, an external, much smarter teacher model steps in. The teacher provides corrective guidance over all the plausible alternative words, enriching the supervision signal precisely where the student model is at its weakest.
This entire interplay between the student and teacher models is visualized here through a conditional distribution of probabilities broken cleanly into 4 quadrants. Let's look at the axes. The y-axis tracks the teacher model's probability, while the x-axis tracks the student model's probability for any given dataset token. Those darker orange colors you see, that represents a higher density of occurrences during the actual training process. By analyzing these coordinates, we can see exactly when and exactly how the teacher needs to step in and help.
So let's break down exactly what happens in those quadrants. Quadrant 1, up in the top left, the teacher is highly confident, but the student is basically clueless. This is where Target-SFT truly shines. The teacher swoops in to rescue the student, correcting its blind spots without forcing that rigid rote memorization. Down in Quadrant 2, the bottom left, both models are uncertain. Here, Target-SFT filters out the noisy label so the student doesn't just memorize garbage data. Over in Quadrant 3, top right, both agree the label is great, so it acts just like standard SFT. And finally, Quadrant 4, the bottom right, the student is already confident, so we naturally reduce the teacher's influence, preserving the knowledge the student already had. It's just incredibly adaptive.
Okay, Section 4, Proof in the Data. Let's look at the undeniable metrics. When we analyze the average at 16 accuracy across 10 different data set in model combinations, it reveals a very, very clear winner. Notice that dark blue line sitting at the very top of the chart? Yeah, that is Target-SFT. Whether it's applied to Quen models, Llama models, small 1.5 billion parameter setups, or much larger 8 billion parameter models, Target-SFT consistently dominates the board. That gray dashed line representing standard SFT, it's basically left completely in the dust, especially when you look at the complex reasoning tasks over on the right side of the chart.
And if we zoom in on specific benchmark victories, the story gets even better. On intense mathematical reasoning datasets, like Numina Math and OpenR1, Target-SFT achieved the absolute highest average accuracy across all the models they tested. Fact is, standard SFT sometimes barely improved the base model at all in math. And in complex medical reasoning benchmarks, Target-SFT once again came out completely on top. It basically proves that carefully designing both the imitation strength and the allocation of alternatives works universally across all sorts of domains.
Now, you might be wondering, why not just use the teacher model for everything, right? Just use a method known as pure knowledge distillation. Well, the data actually shows that using a teacher as a fixed, rigid target is strictly inferior. Pure distillation was beaten by Target-SFT almost everywhere they tested. Because the magic isn't the teacher itself. The real magic is using the teacher adaptively, strictly as a fallback only when the label trust is low. Adaptive fallback is simply greater than rigid targets.
Which leaves us with a pretty thrilling realization. Supervised fine-tuning is no longer just about blindly minimizing some loss function. It's fundamentally about intelligent target distribution design. By totally abandoning rote memorization for adaptive teacher-guided tutoring, TARGET-SFT is proving without a doubt that we can train smarter, vastly more capable AI. So I'll leave you with this. As these models continue to scale up, how will this fundamental shift in post-training unlock the very next generation of adaptive reasoning models? It's a fascinating question, and looking at the data, we are really just scratching the surface. Thanks for joining me on this explainer, and remember to keep questioning the status quo.